Okay, think about this for a second. There's this force, right? And it's so incredibly huge that if it was just a tiny bit unbalanced between you and someone else nearby, I mean, like 1% out of whack, the repulsion force would be strong enough to lift the entire planet Earth.
Mm-hmm.
But you don't feel a thing. It's almost totally hidden, even though it's everywhere. So how can something that powerful be so perfectly hidden in plain sight? Today, we're doing a deep dive into electromagnetism. This is the fundamental force that pretty much governs everything, the stiffness of buildings, the light we see, everything. And our mission, is to really unpack an excerpt from Richard Feynman's classic lectures on physics. We want to pull out the key ideas, make this complex stuff clear, maybe even fascinating, really get into the surprising truths about this force.
Absolutely. It's a great text for seeing how this seemingly quiet force really underpins almost everything. It's huge power, but also it's incredibly delicate balance.
Okay, so let's start right there. The mind-boggling strength and that perfect balance, gravity, right? Force gets weaker the further away things are, following that inverse square law.
Right. Force drops off with the square of the distance.
Exactly. Electrical forces do that too. But, and this is the crazy part, the electrical force is about 1 billion, 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 billion times stronger than gravity.
Just let that number sink in. It's astronomical. 39 zeros.
It's almost impossible to really grasp. But here's the key difference, the really crucial thing. Gravity only pulls, it only attracts.
Mm-hmm. Always attractive.
But electricity, it has two kinds of stuff, two kinds of charge. We call them positive and negative. And the rule is, likes repel, opposites attract.
And that duality, that push and pull, that's the secret sauce. It leads to what Feynman calls the perfect balance. See, in normal matter, like us or this table, you've got pretty much an exact balance of positive protons and negative electrons.
Right.
So these enormous attractive forces and these enormous repulsive forces, they just cancel each other out almost perfectly.
Which is why you don't feel any strong electrical push or pull between, say, you and your chair. The net force is practically zero.
Exactly.
And that balance is just, it's stunningly precise. The analogy I started with, totally real. If you and someone else, just arm's length away, had even 1% more electrons than protons.
Boom. Enough force to lift the Earth.
It really hammers home how perfect that balance is in everyday stuff.
And a direct result of that balance. That's why matter is so stiff, so strong. Think about the Empire State Building.
Okay.
It barely sways, maybe an inch in high winds. Why? Because these electrical forces are locking every atom, every electron and proton rigidly in place. Huge electrical stiffness.
So that's the big picture. But what if we zoom way, way in, down to the scale of just a few atoms?
Well, down there, the balance isn't always absolutely perfect. You can get tiny imbalances, or the distances become so small that the forces get really, really strong locally.
You get these strong residual electrical forces.
Precisely. And that's basically chemistry right there.
Oh, okay.
The forces holding atoms together into molecules, chemical bonds. They are these electrical forces acting in those little pockets where the balance isn't quite perfect or distances are tiny.
But that brings up a big question, something that really puzzled people early on. If positive protons and negative electrons attract so strongly, why don't atoms just collapse? Why doesn't the electron just spiral into the nucleus?
Exactly. Based on the old classical rules, they should collapse. The atom should just implode.
So what stops it?
The answer turned out to need a whole new way of thinking about physics. Quantum mechanics.
Quantum mechanics, okay.
Specifically, it's something called the uncertainty principle. Basically, it says you can't perfectly know both the position and the momentum or speed of something like an electron at the same time.
Right.
So if you try to squeeze an electron into a tiny, tiny space, like right onto the proton, its momentum, its motion becomes incredibly uncertain and, well, energetic. It has to sort of jiggle or buzz around really fast.
Like it can't sit still.
Exactly. It's this inherent quantum motion, this fuzziness that prevents the strong electrical pull from making it collapse right into the nucleus.
Yeah.
Nature just doesn't allow it.
Okay, so quantum jiggling saves the electron. But then what about the nucleus itself? You've got all those positive protons crammed together in there. They should be repelling each other like crazy based on everything we've said. How does that stay together?
Good question. And the answer is, it doesn't use electrical forces to stay together. This is where we meet another force entirely.
Something else.
Yep. We call them the nuclear forces, or sometimes the strong nuclear force. They are not electrical, and they're stronger than the electrical repulsion between protons, but only at very, very short distances.
So they're strong but don't reach far.
Exactly. Their strength falls off much, much faster than the inverse square law of electricity. They really only operate effectively inside the nucleus.
You can kind of see that tension in big atoms, right? Like uranium.
Perfect example. Uranium's got 92 protons. That's a lot.
Yeah.
The electrical repulsion is long range. Every proton pushes on every other proton. But the nuclear force is short range, mostly holding nearest neighbors together.
So in a big nucleus like uranium, the long-range electrical repulsion is almost winning out over the short-range nuclear attraction. It's almost unstable.
It's right on the edge.
Yeah.
And that's really interesting when you think about, say, nuclear energy or bombs.
How so?
Well, if you give that uranium nucleus just a little nudge, maybe hit it with a slow neutron, it can break apart. Fission.
Right.
It splits into two smaller, positively charged chunks. And because the nuclear glue is broken, what takes over?
The electrical repulsion.
Exactly. Those two positive pieces fly apart with enormous energy because of that electrical repulsion. So the energy we call nuclear energy is often, as Feynman puts it, really electrical energy released when electrical forces have overcome the attractive nuclear forces.
Wow. That's a really neat way to think about it. But okay, what about the electron itself? It's negative. No protons inside it to repel. But does it have parts? If it does, why don't they repel each other and make the electron explode?
That is a fantastic question. And according to Feynman, and, well, physics today,
Yeah.
it's a question that has never been answered.
Really? Still?
Still. Trying to figure out the electron's structure, or lack thereof, and what holds it together if it does have structure, that's led to some really deep problems in physics. It's one of those lingering mysteries.
Okay, so these lingering questions and the complexity of moving charges, it sounds like this simple force law wasn't enough.
Right. Coulomb's law for static charges is neat, but when things move, you get delays, you get effects from acceleration, it gets messy super fast. Trying to calculate force directly between moving particles becomes, well, impractical.
So physicists needed a new approach.
They did, and this led to the whole idea of electromagnetism as a unified concept, the force between moving charges. We call that the magnetic force.
But it's not actually separate.
Nope. It's really just, as Feynman says, one aspect of an electrical effect. They're intertwined. Two sides of the same electromagnetic coin.
So how did they simplify it?
By introducing the idea of fields. Electric fields, which we call E, and magnetic field, B.
Fields, okay.
Instead of thinking about charge A directly pushing on charge B, they imagine that charge A creates an influence in the space around it, an electric field. Then charge B feels the force from the field at its location.
So the field is like an intermediary, a condition of space.
Exactly. It exists everywhere. Even if there's no charge there to feel it, it just describes the force that would be there if a charge were present.
So what is a field then, more generally?
Well, think about temperature in a room. It has a value at every single point, right? Yeah. Hotter near the radiator, colder by the window, that's a field. A scalar field, just a number everywhere. Or imagine wind. At every point, the air has a speed and a direction. That's a vector field. Electric and magnetic fields are like that they have a strength and a direction at every point in space, telling a charge which way to go and how hard it'll be pushed.
And does this field idea actually make things simpler?
Immensely simpler, thanks to something called the principle of superposition.
Superposition.
Yeah, it just means if you have lots of charges creating fields, the total field at any point is just the simple sum of the fields from each individual charge. Add them up vectorially. It lets you break down complex situations.
You sometimes see pictures of fields, like with arrows or lines.
Field lines, yeah. They can give you a feel for it, showing direction and maybe density showing strength. But for real calculations, you need more powerful math tools.
Which brings us to
two really important mathematical ideas about vector fields. Flux and circulation.
Flux and circulation.
Flux is basically a measure of how much field stuff is flowing out of a closed surface, like a bubble. Imagine water flowing the flux through a net is how much water goes through it per second.
Okay, but electric fields aren't water flowing.
No, it's just an analogy for the math. For electric fields, flux measures the sort of net outwardness originating from charges inside the surface. It lets you count the charge inside without looking.
And circulation.
Circulation measures how much the field tends to swirl or curl around a closed loop. Think of stirring coffee. There's circulation there. Or water going down a drain.
So it's about rotation in the field?
Kinda, yeah. It tells you if the field lines tend to loop back on themselves. These two concepts, flux and circulation, they turn out to be the keys to describing all the laws of electromagnetism together.
All of them, just using flux and circulation.
Pretty much. These ideas let us write down 4 equations, Maxwell's equations that contain everything.
Maxwell's equations.
Oh.
Okay, let's hear them.
All right. Law number 1, in essence, deals with the flux of the electric field. It basically says the total electric flux out of any closed surface is directly proportional to the total electric charge enclosed inside that surface.
And that implies?
It mathematically forces the electric field from a single point charge to follow the inverse square law we talked about earlier. It means electric influence spreads out perfectly in all directions.
Okay, law 1 connects flux to charge. What's law 2?
Law 2 involves the circulation of the electric field. It says the circulation of E around any closed loop isn't zero if the magnetic flux through the loop is changing in time.
Changing magnetic flux creates circulating electric field.
You got it. That's the principle behind electric generators. Move a magnet near a wire loop, changing the magnetic flux, and you generate an electric field that pushes charges around the wire and electric current. Transformers work on this principle too.
Very practical. Okay, law 3.
Law 3 is about the magnetic field's flux. It says the magnetic flux through any closed surface is always zero. Always.
Zero magnetic flux through a closed surface. What does that mean physically?
It means there are no magnetic charges. No sources or sinks of magnetic field lines like you have with positive and negative electric charges. Magnetic field lines always form closed loops. They never start or end.
So no magnetic monopoles, like an isolated North Pole without a South Pole.
Exactly. People have looked, but none have ever been found. If they existed, this law would have to change.
All right, final one, law 4.
Law 4 is about the circulation of the magnetic field, B. It says the circulation of B around a closed loop is related to 2 things. The electric current flowing through the loop, A and D, and the rate of change of the electric flux through the loop. The second part was Maxwell's brilliant addition.
So changing electric fields can create magnetic fields too. It wasn't just current.
Precisely. That was Maxwell's genius insight. It made the laws symmetric and complete. Before him, they thought only currents made magnetic fields.
Can you give an example of that, a changing E field making a B field?
Sure, think about charging a capacitor 2 metal plates separated by a gap. Current flows to the plates, but not through the gap.
Right, there's no wire connecting them.
But as it charges, the electric field between the plates is increasing. It's changing. Maxwell realized this changing E field acts like a kind of, he called it displacement current, and it creates a circulating magnetic field around the gap, just as if a real current were flowing there.
Wow, so even with no moving charges in the gap, you get magnetism just from the changing E field?
That's the key idea. It was revolutionary. And these 4 laws, plus the law describing the force on a charge, the Lorentz force, that's basically, that's all of classical electrodynamics.
The complete picture.
The complete picture. Though the consequences that flow from these equations are incredibly rich and complex, way more intricate than something like Newton's laws.
You can sort of demonstrate parts of this, right? Like with simple experiments.
Oh, yeah. Pass current through a wire near a magnet. The wire jumps. That's the force law, FQVB. Force on moving charges in a B field. Or run currents through 2 parallel wires. They pull together if currents are in the same direction, push apart if opposite. That's magnetic forces between currents.
And you said magnets themselves are really just currents.
Fundamentally, yes. You can make an electromagnet with a coil of wire that behaves just like a bar magnet. In a permanent magnet, like iron, the magnetism comes from tiny circulating currents at the atomic level, mostly due to electron spin, which is a quantum property.
So it all ties together. And the biggest consequence of these interacting E and B fields
is electromagnetic radiation, light.
How does that work again?
Well, Maxwell's equations show that if you have a changing B field, it creates a circulating E field. But a changing E field creates a circulating B field.
They create each other.
Exactly. One creates the other, which creates the first one again, further away. This self-perpetuating dance of electric and magnetic fields can travel through empty space, carrying energy and information.
No charges or wires needed out in space.
Nope, just the fields themselves, propagating. That's radio waves, light, X-rays. It's literally how we see each other across the room. That light is an electromagnetic wave generated trillions of miles away in the sun, or right here by this lamp.
Okay, but I still come back to this. What are these fields? They feel so abstract, not like pushing a real thing.
And you've hit on a point that physicists struggled with for a long time. People tried to make mechanical models. They imagined space filled with gears or some kind of jelly-like ether that was being stressed and strained.
Like trying to make it tangible.
Exactly. But all those mechanical models, they ultimately failed. They led to contradictions or just didn't work properly. The most effective and arguably the most correct way to think about it is just the abstract field itself. The math describes what happens perfectly, even if we can't build a physical model we can touch.
You mentioned an anecdote about that, McCullough.
Yeah, James McCullough. Back in 1839, he actually wrote down equations for light moving through crystals that were mathematically correct, consistent with Maxwell's later theory. But people rejected them.
Why?
Because his theory described vibrations, but didn't provide a physical thing that was vibrating. Everyone was still obsessed with finding the ether, this medium filling space. His abstract, purely mathematical description just didn't sit right with them, even though it worked. It probably held back progress.
So the abstract idea was actually closer to the truth.
It seemed so. And here's another twist, maybe the biggest one from Feynman on this. Magnetism itself. It's fundamentally a relativistic effect.
Relativistic, like Einstein's relativity. What does that have to do with magnets?
Everything, it turns out. Think about two electrons flying along parallel to each other. From our perspective, watching them fly by, they're moving charges, so there's a current, and thus a magnetic field between them causing a force.
Okay, makes sense.
Now imagine you are flying along with the electrons at the same speed. From your point of view.
They look stationary?
Right. And if they're stationary, there's no current. So according to classical magnetism, there should be no magnetic field. The magnetic force just seems to disappear depending on how you're moving.
Whoa, so the field isn't real in the same way.
It's real in the sense that it predicts forces, but its value, even its existence, depends on your frame of reference. It's intimately tied up with how space and time look different to observers moving relative to each other, which is the core idea of relativity.
Okay, but hold on. If magnetism is relativistic, and relativistic effects usually involve this tiny v²/c² factor, electrons in a wire move really slowly, right? Like millimeters per second. That VC-sec factor must be incredibly tiny, like 10 or something.
It is tiny, yes.
So why isn't the magnetic force between two wires incredibly Rick? We can easily see wires attract or repel. It doesn't seem like a minuscule correction.
That is the stroke of genius. You're right. The magnetic force is a tiny relativistic correction to the electrical forces. But the main electrical forces between the charges in the two wires, the repulsion between the moving electrons in one wire and the electrons in the other, the attraction between the electrons and the positive protons in the other wire, they cancel out almost perfectly.
Because the wires are electrically neutral overall, equal protons and electrons.
Exactly. And that cancellation is far more precise than 1 part in 10 to the 25. It's almost absolute perfection. So you have these huge electrical forces canceling out almost completely, leaving behind
only the tiny relativistic magnetic part.
Precisely. The magnetic force dominates purely because the much larger electrical forces have vanished due to near-perfect charge neutrality. It's like having two giants pushing equally on opposite sides of a door, and the only thing making it move is a tiny mouse leaning on it.
That's amazing. So we only see magnetism clearly because electricity hides itself so well.
You've got it. And think about the historical implication. This near-perfect cancellation allowed physicists to study magnetism, a relativistic effect, and work out Maxwell's equations, which are correct up to relativistic terms, before anyone even understood relativity.
So when Einstein came along with relativity,
the laws of electromagnetism didn't need changing. They already had relativity baked in, implicitly, because magnetism is relativity revealed by the cancellation of the main electrical forces. It's quite profound.
Okay, let's pull back for a moment. Thinking historically, for thousands of years, all humans knew of this vast electromagnetic world was basically static cling and magnets.
Pretty much. The ancient Greeks knew rubbing amber made it attract bits of papyrus, and they knew about lodestones, natural magnets, attracting iron. That was about it.
And the reason they saw so little...
Again, that fantastic precision of the balancing of charges, the main effects were hidden.
But now we know better. We understand that chemistry, materials, even life itself...
Life itself are to be understood in terms of electromagnetism, as Feynman says. The forces holding molecules together, nerve impulses, muscle contractions, it's all electrical forces at work.
And once we did grasp the laws, wow, the technological explosion.
Unbelievable. Telegraph, telephone, radio, electric power. Think about a modern power grid. Feynman uses this image of a single great water wheel, a power plant connected by thousands of branching filaments, wires powering 10,000 engines in 10,000 places, all running on these invisible forces understood through Maxwell's equations.
And today, we manipulate even tinier, more subtle effects, like a TV antenna.
Right. Think about it. You've got a thin metal rod, and just by how electrons are sloshing back and forth in that rod, induced by incredibly faint radio waves,
we can reconstruct a detailed image and sound from potentially hundreds of miles away. We can tell what a man is doing by the way he affects the electrons in a thin metal rod hundreds of miles away.
the precision is just mind-boggling. It's built entirely on understanding and manipulating these subtle electromagnetic effects.
Which leads Feynman to that really bold claim about history.
Yeah. He says, looking back from, say, 10,000 years in the future, the discovery of the laws of electrodynamics by Maxwell will likely be seen as the most significant event of the 19th century.
More significant than huge political events like the American Civil War, he says.
From a long-term perspective of fundamental understanding and its impact on humanity's capabilities, he argues, yes, it fundamentally changed our relationship with the universe.
So, wrapping up this journey, we've seen this force, electromagnetism, immense power yet hidden by perfect balance, shaping matter, driving chemistry, underpinning life, and all our technology.
And delving into Feynman's insights really highlights how sometimes the most abstract concepts, fields, flux, circulation, even relativity hiding in plain sight, turn out to be the best, most accurate ways to describe the deep reality of the universe.
It definitely makes you think, given how this amazing balance of electrical forces allowed a tiny relativistic effect, magnetism, to become so important, it leaves you wondering, doesn't it? What other fundamental forces might be out there, maybe perfectly balanced or seemingly insignificant right now, just waiting for us to find the right perspective, the right conditions to reveal even deeper secrets about how everything works.